Hello everybody. I wanted to go through the review sheet for Monday's quiz on parametric equations and vectors. So we did 1 through 7 and you had an opportunity to work together with somebody else on those on class. So I think I'll just do 8 through the end. And I'll walk through what I did and you guys can see if you have any questions. So number 8, we have the position of a particle. We have parametric equations for the x and y coordinates. And then it says for what values of t is the particle at rest. So I know that the particle will be at rest when both the velocity in the x direction and the velocity in the y direction are 0. So if only the velocity in the y direction is 0, then it's just going to be moving horizontally. And if only the velocity in the x direction is 0, then it could be moving vertically. But we want to have both to be at rest. We want it not to be moving left or right, nor to be moving up or down. So we want both the derivative with respect to x, or of x with respect to t, to be 0, and likewise the derivative of y with respect to t to equal 0. So that's a long way of saying that first sentence there. So we find the first derivative using the functions that were given to us in problem 8. We set those derivatives equal to 0. The first one and the second one will both factor. We can take a common factor of 3 out of both. We can factor into the dx dt when I divide both sides by 3, and factor becomes t minus 3, it's t plus 2, so the 2 times when the particle will not be moving left or right because the x dt is 0 is going to be at negative 2 and positive 3. Likewise, when we set the dy dt equal to 0, divide by 3, we'll get that t is either 1 or 3. So the only time when both dx dt and dy dt is 0 is at 3. So t equals 3 should be the correct answer for question number 8. For question number 9, it says we have parametric equations. Write the equation of the line tangent to the curve at the point when x is 8 and y is 4. So the equation of any line can be written in the form y minus y1 equals the slope times x minus x1. They gave us that x is 8 and y is 4, so we can substitute those in. And the only thing we have left to find then is the slope. And we know to find the slope, we want dy dx. So we're going to find dy dt. We're going to find, since y is equal to this, dy dt will be that. We're going to find dx dt, and we will have this. Now, they told us that x was 8, which implies that y is 2, because x equals t cubed, so 8 equals t cubed, and t would have to be 2 to solve that. They also told us that y was equal to negative 4, and the equation for y was this, so that means that y will equal negative 4 when x is 2 or when t is 2 or when t is 3. So the point that those two have in common is t equals 2. So we're looking for the slope, dy dx, at the point when t is 2. So if we plug 2 back into the derivative for x here, the derivative of x with respect to t is 3t squared. Plugging in 2, we'll get 3 times 2 squared, or 12. Likewise with the y, its derivative will be 2t minus 5. Plugging in 2, we'll get 4 minus 5, or negative 1 for dy dt. Dividing those two things will give us negative 1/12 for dy dx. So negative 1/12 will be our slope. We've got our x value to be 8 and our y value to be 4. So in point slope form, we'll have the equation of the line that you see here. Question number 10 on our worksheet. We have a particle whose position is given by the parametric equations that you have here. Find the velocity of the vector when the particle's position in the horizontal direction has an x-coordinate of 25. So we can set the equation that we have here for x equal to 25. And we can solve for t. And that will give us when this tells us when t is equal to 5.446, that is the point, that is the time when the x-coordinate is 25. And you can draw the graph of this function, making sure you're in radian mode. And you can draw the graph of y equals 25, making sure you're in radian mode. So you're going to be back in regular function mode, not parametric. You're just going to graph this in y1, this in y2, and see where they crash into each other. You'll find that point to be the place where they run into each other. So our job here in question number 10 is to find the velocity vector. So if this is the position of the x-coordinates position, then its derivative would be this. And when we plug this value of t that produces an x value of 25 into this equation, we have the in the x direction, or in the horizontal direction, the horizontal component of the velocity vector is 7.0081. We're going to play the same game to find the vertical component of the velocity vector. Here we've got the product of two things, so we're going to take the first factor times the derivative of the second, plus the second factor times the derivative of the first. We're going to plug in the t equals 5.446, and that will produce dy dt at the moment when x is 25. Now if we divide dy dt and dx dt, that will give us, if we write that in vector form, this is the horizontal component, this is the vertical component. So the velocity vector when x is 25 will be the velocity when the vector when time is 5.446, which will be the horizontal component and the vertical component that you see here. Again, this would be a calculator question, because in order to solve the equation that you see right here, we needed to use our calculator. Question 11. Question 11 talks about the magnitude of the velocity vector. So we need to find the horizontal component and the vertical component of the velocity. So we're going to need to find dx dt and dy dt. And once we find dx dt and dy dt, we'll plug in 5. That'll give us a vector, the components of our vector, at t equals 5, and then we can just do the Pythagorean theorem to find the magnitude of that vector. So when time is equal to So here we are with question number 11. The magnitude of the vector will be dx dt squared at 5 plus dy dt squared at 5, and then take the square root. I found dx dt, plugged in 5, and squared it. I found dy dt, plugged in 5, and squared it. And so the square root of 2600 will be the magnitude of the velocity vector. For part B, it asks us to find the length of the curve, the distance traveled along that curve between time equals 0 and time equals 5. So we've got the square root of the change in x with respect to time squared plus the change in y with respect to time squared, and then we want to integrate that from 0 to 5. We've already found dx dt. We've already found dy dt, so we can square both of those, add them together, factor out the common factor, and we'll be left with something that looks like what you see here. Now we can do a u sub. U will be the stuff under the square root. Then we can rewrite our original integral that would give us the distance traveled, as this would become u to the 1/2. The stuff that's left is du. When we increase the power by 1 and divide by the new power, then we'll have 2/3 of u to the 3/2. Our original limits were 0 and 5, but when we change to u's, when t is 0, u will be 1, and when t is 5, u will be 26. We plug those in. We'll have the square root of 26 cubed minus the square root of 1 cubed. and that will give us what you see here. And that would be the distance that that particle would travel as it moves along the curve from time equals 0 to time equals 5. Question number 12 is going to go the opposite direction of what we've been talking about here. It gives us dx dt and dy dt, and they ask us to find the coordinates of the point in terms of t. So with question 12, if we were to integrate dx dt, that would give us a function of x. So if we integrate 1 over t plus 1, get the natural log of the absolute value of t plus a constant. We know that when t is 1, x is the natural log of 2. So if we substitute in t equals 1 and x equals the natural log of 2, we're going to get that that constant is 0. Therefore, this is the parametric equation that gives us the x-coordinate of the position of the particle. Likewise, if this is dy dt, when we integrate that, this gives us a function y in terms of t. We have a plus c here, and we know that when t is 1, y is 0. So if we plug in 1 for t and 0 for y, we get the constant to be -1. So this would be the parametric equation for y as a function of t. Then they asked us to write y as a function of x. So if I know that these two things are true, if I can solve this equation up here for t, I can plug that into this equation. I'll have y as a function of x. So let's focus on taking this equation and solving it for t. So I'm going to exponentiate both sides to get this. T is a positive number, they told us in the problem, so t plus 1 will be positive. So I can drop the absolute values, because the absolute value of a positive number is itself. And that gives us what you see here. That means that t will equal x to e to the x minus 1. And we can take our equation for y, replace the t with the e to the x minus 1, multiplying that out, combining the like terms, gives us y as a function of x. I believe we did part C, the average rate of change of y with respect to x when t goes from 0 to 4. I don't know if we did it in class or if we just set it up, but basically you're doing change in y over change in x. We're going to plug 4 into the y equation here, and that will give us 15. We're going to plug 0 into the y equation. That'll give us -1. So our change in y is going to be 15 minus a -1, or 16. Our change in x will be this equation evaluated at t equals 4, which would be the natural log of 5, minus this equation evaluated at t equals 0, which would be the natural log of 1. So 16 over the natural log of 5 is what we would have there. And finally, they said find the instantaneous rate of change of y with respect to x when t is 1. So dy dt divided by dx dt. Well, dy dt, we knew what dy dt was here at the beginning of this problem. Dy dt was 2t. So dy dt when t equals 1 will just be 2. And we knew that dx dt was 1 over 1 plus t, so when t is 1, we'll get 1 over 1 plus 1, or 1/2. So the 2 that we have in the numerator divided by 1/2 will be the same as 2 times 2, or 4. So that would be our instantaneous rate of change for 12D. I'm going to pause the video now, and I'm running up against the 15-minute deadline, so we'll do 13 in a separate video.